Welcome to another edition of Math for No Reason. In this edition, we will tackle this problem from group theory. Suppose we consider the set R star, which is all the real numbers except 0. Then R star under multiplication is an abelian group. And if we consider the function phi, which is from R star to R star, given by phi of x is mod of x, then phi is a homomorphism. And finally, we will try to find the kernel of this homomorphism. So there are quite a few terms which we will introduce as we proceed. So let's begin with part A. So to show a group, we have to show a couple of things. If we take two numbers xy, which are non-zero reals, then x into y is also a non-zero real number. It can only be 0 if one of these x and y is 0. So therefore, if both x and y are not 0, then xy is also not 0. So therefore, this is closed under multiplication. We also know for reals, xy is equal to yx. So this is commutative. So the multiplication operation is commutative. We also know from basic high school algebra that x into y into z is xy into z. So the multiplication operation is associative. Note that whenever we are writing xy, we are actually meaning x into y with this multiplication operation. We should have written it all in that manner, but we chose to use the usual approach. Now, if x is a real number which is not 0, then we know that if we multiply that with 1, then we get x, and also this is true. So x into 1 is equal to x is equal to 1 into x. Therefore, 1 is the multiplicative identity, or rather in this context 1 is the identity element. And if we take any non-zero real number, we know that 1 by x is again a non-zero real number, and x into 1 by x is 1, and that is 1 by x. So we see that for every x in R star, there exists 1 by x which also belongs to R star, such that x into 1 by x is equal to 1 by x into x is equal to 1. So this 1 by x is the inverse element of x. So this proves that R star with multiplication is an abelian group. So we are done with this. Now let us look at part B. So what is a homomorphism? In the context of group theory, we say a function phi is a homomorphism if it preserves the group operation. That means in this particular case, phi of x into y, which we can shorten and write as phi xy as I mentioned before, this is phi x into phi y, which is in short notation phi x phi y. So if this property holds, that phi of xy is equal to phi x into phi y, we say that the function phi is a homomorphism of groups. Now here this phi is given a form, this is true in general, but here phi is given as mod x. So let us check whether mod x has this property. The LHS phi xy is mod xy, and we know that that is by property of the absolute value. This is mod x into mod y, and therefore we can write this as phi x into phi. So we can conclude that phi is a homomorphism. For the third part, we need to know what is meant by the kernel of a homomorphism. So in this particular case, this would mean, so we are looking at all x in the domain of phi which are mapped to the identity element of the range. So here both the domain and the range are the same set, so therefore there is a lot more simple structure here. But the notion of a kernel is true even when we are dealing with two different groups, say G1 and G2. So kernel would mean the set of all elements which are in the domain of the homomorphism which are mapped to the identity element of the group, which is the range. Now, here this will mean that phi of x, which is mod of x, is equal to 1. So what values of x are there which gives mod of x equal to 1? And we know that this can happen for only two numbers, 1 and -1. So therefore, the kernel of this homomorphism is the set 1 and -1. It's a good point to stop. Thank you.